So our last but not least part of this track is a panel discussion about industry applications. And when we were building this track, we started with Yarden's talk from PayPal, demonstrating how he got out of his raw data more using RNN. We were then happy to find out that other companies have also experienced implementing deep learning over tabular data, also over temporal data, like Yarden. We thought it can be interesting to finish by going a little deeper and understanding what are the similarities and differences between all the different applications. I'm Sharon Datner, principal machine learning scientist in PayPal, leading the modeling guild in the fraud detection domain, and actually a user myself of Yarden's model. With me today are, I'll share my screen for that. Andrey Nikitin, data scientist at Wix. Cohen Maimon, AI cyber architect at NEC Israel Research Center. And Yarden Raiskin, senior machine learning scientist at PayPal. We'll start by hearing short highlights about the applications of Andrey and Maya, followed by a panel discussion. So feel free to also submit questions yourself, and I'll try to incorporate one or two depending on time, as always. Andrey, go ahead.
Thank you, Sharon. Second. Oh, great. So can you see my screen? Hi, everyone. My name is Andrey, and we'll be talking about predicting business KPIs using temporal user actions. Few words about myself. I'm a data scientist at Wix, and I'm also part of the Y Data program as teaching assistant in a deep learning course. So first, let's talk about what the business KPI is. It can be a premium purchase. We want to know whether a user is actually going to buy a premium package. It can also be churn rate. We want to know whether a user is going to leave the platform in the future. But it doesn't have to be related to money. It can also be adding a specific functionality to your website, like connecting Google Analytics. Now that we know what a business KPI is, we can talk about how to predict them. And in this example, we'll talk about premium prediction that we use to optimize our email marketing so that we don't spam our users with irrelevant emails. In a typical predictive setting, we have a user registration. We set some prediction point, in this case, 1 to 7 days after user registration, which means that we have 7 different cohorts, 1 for each day of the user. Additionally, we would also have to set some kind of target, the horizon for the user to actually become premium. And this can be any target. It all depends on your use case. So here I selected 28 days. Now, let's take a look at how first week of the user in the platform can look like. The user signed up on Sunday. She started working on her website, adding images, text, adding the website, kept working an additional day, then did nothing for the next 2 days and went back to it on Thursday, did some minor changes, and finished working on the website on Saturday. Now, on a typical setting, we would take this data and aggregate it to a table. And then we would take that value and use it as a feature for our predictive model. The problem is that by doing so, we actually lose the temporal structure of user actions. We don't really know when the user did what and at what frequencies. Additionally, after having a single model, single cohort, I deploy additional models for additional cohorts. Now, sometimes I want to increase the number of cohorts that I want to predict for. And that's not that scalable because I would have to add additional models. So I propose to do something generic for the sequence data. In this case, I have 3 different users of 3 different user ages. They're all serve as the same input to the same RNN layer. And I do it by using masking. Now, masking is quite popular in language models, and I use it here to mask the missing values of different cohorts. To illustrate the concrete example, let's take a look at a single feature, count the number of times that the user edited the website. So the sequence for the three different users would look as follows. Each value in the sequence would have correspond data point based on the cohort age, and the rest of the values would be masked. So the next day, it would have an additional data point because our user has an additional age inside the cohort. The general model architecture would look as follows. We would have our aggregated user actions on some kind of divided on a time frame. I use daily, but it can be on any time frame, hour, months. It all depends on your use case. For the categorical features, I use categorical embeddings, which is very simple yet very effective way to represent categorical features in a neural network. And for the continuous features, I use a simple dense layer. And I concatenate the three types of input to a single vector, and the single vector being optimized on my supervised objectives, premium or not premium. Now, why does it work for us? It's a single generic model that is able to serve multiple cohorts. We can actually take the user embedding from inside a model and use it for downstream tasks, the same way we've heard from Yarden's talk. And because of its neural network, we can actually do an end-to-end learning and add an additional inputs to the model. For example, take images from the user website and use it also as an input. Thank you.
Thank you, Andrey. It's really nice to see how you were able to use similar tools, RNN, embedding categorical features to a totally different domain. And I wonder, what do you think are the main differences between your approach and Yarden's approach?
So I would say that if we take one extreme, and this is aggregating a single value in a table, and the other extreme is what Yarden is doing, is actually generating the sequence of the actual events. What I do is something in between. I still aggregate the values, but I do it partitioning. I partitioned it on some time frame. In my case, it's days. So I still have this temporal structure of the data, but it doesn't represent the actual events themselves. I'd imagine that Yarden's approach would lead to more accurate representations because it's the actual reality, it's the actual events themselves. But on a technical perspective, it would be much harder to implement.
Got it. So I would say the main difference is on the input level, meaning what do you do before you put your input into the model. You aggregate it based on different time frames, like you said, while Yarden is using raw data. Nice. Yeah, exactly. So, Maya, can you share your highlights before we'll go to the discussion?
Sure. Thank you, Sharon. Hello, everyone. Good afternoon. My name is Maya, and I'm AI and Cyber Architect at NEC Israel Research Center. Today, I will present stock exchange data models. The models were developed as part of privacy research done in my teams during 2020. You can see our center at the right. We are doing cutting-edge innovation in cyber protection, deep learning, and AI. The global NEC is a Japanese company that exists over 120 years. First, let us see the data we work on. Transactions at the stock exchange are recorded in orders and deals tables with some features. The order tables at the top has two requested actions of sell and buy of some securities. For example, order to buy stock or share. The actual deals that have succeeded are at the deal table below. The data in his research is real public data from the Israel Stock Exchange with one addition. We have an ID of traders that did the actions. This is confidential data and cannot be publicly available due to privacy concern. The data was given to us as a cooperation with several Israel authorities as part of research in privacy. One analysis approach is computer archetypes of traders. There are different types of traders at the stock exchange. You can see the pie on the right. The variety depends on many parameters. There are small private traders and more sophisticated ones, one big, one small. The buy and sell actions we saw on the previous slide implies the classification into the different groups. Clustering traders can reflect behavior across time. We can see when traders are doing similar actions or when their strategies are changed. We use mathematical embeddings to represent the traders. Basically, each trader is represented with vectors, when similar traders will have close representation in some of the vector dimensions. Such temporal representation is very useful. It can give an initial flag of prices and market changes and performs as market stability estimator. The market decomposition allows market analysis that can be published regularly and help the finance decisions. The initial approach to cluster traders is autoencoder self-organizing map model. This is the first one. We'll see a more advanced one in a second. The input is trader features like number of transactions per day, average volume per day. The autoencoder compresses the inputs to the few neurons at the middle layer. These few neurons are the input to the self-organizing map or SOM. SOM maps the input into clusters, 6 clusters in our case, you can see at the right. The clusters are temporal, for example, per day. Although they have reflected some anomalies, this representation has not captured enough effects of the complicated finance world. The second approach is more advanced and is based on NLP methods. We learn an embeddings representation of all finance actors, traders, securities, like shares, and market snapshot. First, transaction data is modeled into graph that is depicted on the temporal bipartite graph at the right. One side of the graph is traders, while the second side is security with some important features, like volume of the transaction. Connection between traders, like trader CI and security SJ, means the trader has bought some security, say share, SJ, at the time interval. Later, we use random walks to create paths on the graph, like sentences in a document. Triplet loss learning is used in training when security and traders' vector representation are closer if they have something in common, as expected. This learned representation can be utilized for various tasks, like anomaly detection and financial understanding. Specifically, we have automatically detected irregular behavior at the Israeli market following the discovery of the natural gas.
Thanks, Maya. So we can see again that you had to manipulate your data a little bit differently to build a graph to begin with before you trained your model. And we saw that all of you had to work a little, right, to work your models, to use deep learning. So I think the questions that come up to mind is, what was your main motivation to actually use deep learning if it's a little bit harder? Maya, maybe you can start.
Sure. Stock exchange data is being thoroughly researched, but it's just transaction, and there is no simple algorithm on how to use it. Deep learning, specifically embeddings, will provide us a way to understand the traders and the market and show how they operate. Another reason we have is part of that this work was part of privacy research, and deep learning can be used with privacy methods.
It's interesting to see that something that is many times is the caveat of deep learning. It's hard to understand. Now it's useful for privacy. Andrey, what about you? What was your main motivation to use deep learning?
So mainly it was two. The first one to actually introduce the temporal structure, because I had this idea that the changes between time is actually what's important and not only the values themselves. And the other one was the technical one. I actually wanted to have a single model instead of kept on adding additional models to production.
Okay, nice. So you were able to use just one model instead of many using deep learning. Yarden, what was your main motivation?
So when we got started, we didn't get started with deep learning. We started with simple techniques such as TF-IDF over n-grams of events. And we also looked at other approaches such as Markov chains and others. But what we saw is that they were all lacking because our goal was to find a useful representation that is general purpose that can be used over several models or several machine learning tasks. And we can't necessarily tell ahead of time what all the possible states are. So we can't go through, let's say, Markov chains. And we kind of explored different architectures, and we were trying to come up with ways to fully utilize all the data that we have, process it sequentially along with the other features, and that kind of led us into looking into RNNs.
So maybe it's not a coincidence that all the applications are over temporal data. Seems that this is a very good fit. So all of you touched it a little already, but I want to give you opportunity to talk a little bit more about it. Andrey, what were your biggest challenges with your specific data?
So I would say that the main challenge was to actually how to represent in a single sequence different cohorts, because there are different ages. Like when using an RNN, the sequence you have to have some kind of upper bound, right, for your sequence. And let's say, I don't know, it's 7 days and you have a 1-day cohort. So what do you do with the rest of the data? So finally, after working a little bit on it, and that actually seeing that the masking actually worked and I have good representations and I have good results, so the rest was pretty much easy.
Got it. So for you, it was challenges that were about how to use the same model for different type of users. Yarden, what about you?
So our challenges were both from the scale of data perspective and from what type of data we have to work with. The scale, I think Andrey also touched about it in his answer. Just gathering the data and figuring out how much data we want to look at. Deciding on the time window and other parameters that we can go into the details. That was one very big challenge, also from an engineering perspective. The other challenge was how we can describe all of our raw features in numeric terms. So in my talk, I mentioned a few kind of simplistic examples and how we can approach them. In reality, we have lots of different types of features, and we will need to apply a certain policy to each type of feature separately. So in coming up with both matching those policies and coming up with them was not a trivial task.
So I think one of the main parts of you guys' work was the pre-processing stage. Maya, can you maybe share a little about what you did?
Sure. We have two important pre-processing steps that we had. The first was noise reduction. In this research, we use only active traders who make at least some transactions per day. The second one is transaction aggregation per traders, for example. In the stock exchange, the market liquidity is low. So traders tend to place several small amounts of transactions instead of just the one. This causes bias during training towards these transactions, and so we reverse this process to avoid this bias.
So yet again, we hear about aggregations that we need to do before we start training our model. Andrey, what was your pre-processing stage?
So unlike tree-based models, neural networks are very sensitive to numeric numbers, right? And you need to be much more sensitive to things like, I don't know, outliers, big numbers, high cardinality features. We heard 2 talks just about it, right? Talking about how to actually handle high cardinality categorical features. And I think that's also like maybe part of the current conception that neural networks can do well on tabular data, but only because we are used to working with based models that works really well with any kind of data you give them. So yeah, you have to be much more sensitive in handling the extreme cases, add very heavy regularization inside your model. So even if it's simple on like dropout, but do more than less. That's for sure. That's like what made a difference for me.
Got it. So in your pre-processing stage, you also made sure your data is contained, I would say, not pulling your model to any way. Okay, so one word that we all keep saying, I think from the beginning of this track is embedding again and again. So how do you evaluate them? How do you know that you have a good embedding? Yarden, maybe you can start.
Sure. So that's a great question in our case, because our goal was to create general purpose features that can be used across multiple machine learning tasks. So there's a bit of ambiguity when we say what good embedding means. So I can break it down into 2 parts. The first part is whether or not the autoencoder works well. And the second part is, are the resulting embeddings useful? So as for the autoencoder part, I think it's pretty easy because we feed an input, we generate an embedding, and then we feed it into the decoder, and we reconstruct the input. So as long as our reconstructed sequence is similar to our input, then we're doing well, and we can measure that using the reconstruction error. So that's one part of the question. The second part is, are the embeddings useful? So the way we tested it, because it's a hard question because we want to generate general purpose features, we actually tested these features on a large population using quite a few labels that we had available to us. And we trained multiple classification models on top of our embeddings that we froze for this task. And what we wanted to get, so a good performance in this case would be to perform well on most of the use cases and not perform exceptionally well on one or a few cases and bad on the others, because we wanted to make sure that we are able to summarize the user behavior well, and that it applies for multiple classification tasks. So that's how we basically wanted to see that it's useful for multiple classification tasks.
Interesting. So you said that you have one way is just, let's see that actually we can use these embeddings to extract again the original data and measure the reconstructual error. And the other part is to see if it's useful, if we can use it in many different models and many different applications.
Exactly.
Nice. Maya, how did you evaluate your embeddings?
Well, for the stock exchange data, I can share 2 validation steps. The first is stability. If a trader is from the private sectors doing only a few transactions per day, in the clustering, it should remain the same for days, for months, and probably forever. The second one is to check if the embedding and learned information we do know, but we have not introduced it during training. If we examine the trader behavior, we can see that many traders prefer to trade securities from a single market. For example, real estate or high tech, they aim to achieve proficiency on that market. Another trader properties could be the security type, like shares or convertible. Both trader characteristics were learned automatically and have been differentiated between the clusters. It means the embeddings were strong enough to capture this information, although they weren't aware to it during training.
So you have something that is like outside of your main model. You have the clusters, and this is actually sort of tagging, I would say. It's not a tagging, right? It's not a label, but the fact that you can each time see how your embeddings are going to the different clusters can help you validate your embeddings.
Yes, it's even automatically because embeddings are more or less vectors in space. So clustering means that we can do different kind of clusterings in space. So it's kind of automatic way to do
it. And Andrey, in your case, how did you evaluate your embeddings?
So in my case, it was very easy. I didn't because I have a supervised task, right? And I had some baseline of performance and I knew where my model should be. But because it's a supervised task, I can assume that if my model performed well, the representation I take, right, the embedding I take from inside a model could serve as a good representation, like for user engagement, because I have a good performance on my supervised task.
So maybe it's interesting to test if those embeddings are useful to other cases, like it was for Maya and Yarden. So another thing that I think we haven't touched yet, not thoroughly, is around explainability. This is always one of the main gaps that people are saying, okay, once you move to a deep learning architecture instead of tree-based model, you lose explainability. So how did you guys overcome it? Yarden?
So explainability is a whole field, so I'll keep my answer short. So I can say that we had multiple users of our embeddings, and some of them just explainability was not something that's important for them. For them, if they test the features and the features perform well in the model, then they adopt the features, and that's good enough. In other cases where we had to explain, at least in some capacity, what each embedding coordinate means, we have actually developed a process that is able to explain each of the embedding coordinates. It's a very cool process, but unfortunately, I can't elaborate on that because we're in the process of patent filing at the moment. So maybe we can talk about it next year.
Maya, what about you? How did you overcome this challenge of explainability?
In our case, it was the opposite. The stock exchange data is very complicated, but it's just transactions. So having the representation can help to understand the market. So we don't lose information we know. It's the opposite. We get information.
So I think we have time for a question from the audience. One of the question is regarding feature selection. They say rightfully that feature selection is much less emphasized when working in deep learning models. And they were wondering, what is your approach regarding feature selection? Andrey, do you want to start?
Yeah, sure. Again, I started with from simpler models, right, from the tree-based. So I had this a beginning set of features. what was interesting to see when I did the neural network and during training, when I looked at the weight distribution, if you remember the architecture of my network, I have the sequence and I have also the continuous features. And what I learned there that almost nothing happened in the continuous features. So I can probably drop it and the sequence will still have most of the information there. So it's one good way to actually approach it, is to actually, look through the training, through the epochs, and to see what actually is happening instead of relying on the end result.
Got it. So your training was like in different iterations. And first iteration, you were able to use it also for feature selection.
Yeah.
Maya, how was your feature selection process?
At the beginning, we started with some features about the traders. Like I said at my slides, number of transactions, the amount, average amount per day. So some different characteristics, and we learned some embeddings about it. It just like in tests, we decided what features are helpful. But as I said, the embeddings that were learned on the features were not enough. And we had to go to temporal data models to get more information.
So in your case, you didn't really need to have feature selection because there was not enough features.
We did, but after some point we decided, well, this is not enough. Let's go to another direction.
Deep learning likes more data.
Yes.
What about you, Yarden?
So once we've trained the entire process to generate embeddings, we evaluate it as per the method I described earlier. We actually kind of push the feature selection problem to the end users, because our goal is not task specific, and feature selection is typically a task specific task. So we basically say, hey, this is a user embedding that is well, and what the downstream models will do, they will just take all the features and then perform their own feature selection, and they'll take those features that are useful for them.
So in your case, the users were actually the ones that did the feature selection.
Yeah.
Okay, so thank you all for sharing your work and insights. So we had Maya and Yarden, and they both faced unsupervised problems, one in the fraud domain and the other in the stock market. They both used deep learning, and it helped them to capture a lot of insights about their data. Maya used the graph, and Yarden used our RNN. While Andrey also used RNN, but for a supervised task, since it enabled him to have a more generic model over a group of different use cases. All face the rigorous stage of pre-processing their data, which probably required more effort than using a tree-based model. But once they did, they were able to achieve highly useful generic multi-purpose data representations. Thank you, Maya, Andrey, Yarden, and of course, all the great speakers of this track, and all the viewers who made it to the end. Thank you. Bye.
Thank you.